the problems. Right, I just started with the exercise, and yeah, the first section was boring. That's all I gotta say. But this one, it doesn't look boring. I mean, I tried a few, and it doesn't look boring at all. I didn't like really like complete any problems, so it's still completely new for me, but I looked at it at least. So first question is, for a string, the reverse of the string return W reverse is the string W, of course. For any language, let AR be the reverse of all strings in A. Show that if A is regular, so is AR. Well, this is very elementary, but it's just the first problem. So yeah, I mean, come on. You have a machine, and then it has like some. So we're talking about regular languages. That obviously means we can think of it in DFAs. So you have like some machine, it has some stuff, whatever it does, and then eventually it comes to a final accept state or multiple accept states, and it starts with an initial state, right? Yeah. So we can also like what we can do is um, think of it not as a DFA, but also sort of as an NFA. Like if these are all of the final states, right, you can combine each of that into one final state, right, and then say that okay, it just has one initial state and then one final state. Cool. So now what we would want to do is go in the reverse direction. That is, these are the initial states now and these are the final states, and every single arrow is reversed, right? So yeah, and that I claim is going to give you the reverse of the language. And I'm not even going to like prove it formally, because I suppose this is like done at this point. But also we could do it in a different way, like using induction sort of. Suppose your like whatever, so you think of regular languages, these can be generated using regular expressions. Suppose your regular expression is either of this form, R1 union R2, or it's R1 concatenated R2, or it's R1 it's intersection R2, or if it's R1 star, right? Yeah, if this is like your regular expression, then the reverse of this language, that's also just R1 reverse. So the reverse of the language which R1 provides, union R2 reverse, right? And it's easy to see that because like R1 generates some language, R2 generates some language. This is the union of that. So the reverse of those languages, the reverse of that union is going to be the union of the reverse of languages. Easy, right? Similarly with the concatenation, you just have like R2 reverse and then R1 reverse, right? And so I'm saying that if these smaller languages, if they are regular, then this will also be regular, right? If this part is regular and this part is regular, then concatenation is regular, and so you're done basically. Similarly, the reverse of this would just be something like R1 reverse intersection R2 reverse, right? Reverse. And then R1 star, yeah, the reverse of that is basically just R1 reverse star. Makes sense. Yeah, and since now this would be a regular language, our induction stuff, that just means that this would be a regular language, complete thing. So yeah, essentially any regular operation that you do, that like on the reverse languages also give you regular languages. So by induction as well, you can easily prove induction on using regular expressions. You can easily prove that yes, this does work. So 31, that's like done. 32, it's slightly harder. Actually, it's much harder. So sigma 3 is this set. So these are column vectors, and these are like in binary sort of. There's only 0 or 1 over there. Right, and sigma 3 contains all size 3 columns of zeros and ones. A string of symbols in sigma 3 gives 3 rows of zeros and 1. Consider each row to be a binary number. And so what they're meaning by all of that is, suppose you have a string, I don't know, maybe you have something like 0, 0, 0, and then you have 0, 0, 1, and then so on. Well, maybe till like 0, 1, 1. Then this whole thing, this is a row of the string. So this is the bottom row and these two are the top rows. So the sum of these two top rows, that should be the bottom row. And we don't mean like logic sum, like not pairwise sum modulo 2, we mean sum these as binary numbers, right? So suppose you have 0 0 1 over there, that means it's 1. You have 1 0 0, it's 4, right? And then when you sum that, it should be 5, so it should be 1 0. I mean, this was actually logic summation, but like if you had something else, if you had 0 1 1 over there, so 0 0 1 over there, then this would be 0 1 0. That's how it would be. Okay, so yeah, we want to prove that this language, which is all such strings such that the bottom row is the sum of the top two rows, that is that's a regular language. So they're saying work with the reverse of the language and then show that the reverse of that is in fact a regular language, so using the 31 thing. So let's think about it. Bottom reverse, now how do you deal with that? Well, how do you add two binary numbers? First of all, suppose you had like 1 0 0 1 something, and then you have, I don't know, 0 1 0 1 1 something like that, right? How do you do that? Well, you do it pairwise first. So 0 and 1, add that to get 1, and 1 and 1 add get 0, and then you carry on something. So first we'll need to store this carry on stuff, right? In any case, yeah, right. So what's like going to be our delta function? It of course takes sigma 3 star, like, yeah, that's not right, sigma 3, right? It takes stuff from sigma 3, the alphabet, and then whatever states we decide, and then it gives some other state. We want to construct a DFA basically. Now I want to simulate addition by this thing. So one of our states will be a carry state, one of our states will be a reject state. So we'll have a Q reject, a Q accept, a Q carry, right? And what about the other states? So yeah, Q carry, that's like, how do I even say this? Yeah, this is gonna be weird. So you don't have like ways to store stuff, right? You don't have ways to, like, yeah. So we'll just have to duplicate the whole machine basically. It's kind of complicated. Oh, come on, think about it. Well, yeah, I mean, it shouldn't be that hard. So either you carry with a 1 or not. So Q carry 1 and then Q carry 0. These are two states which represent that. So whatever your next addition you'll be doing, you will be doing it with a carry or without a carry. So if you're doing it with a carry, then the transition function will be slightly different. I mean, the transitions defined for this will be slightly different. So the transition should be something like, so if you're doing it without a carry, it's just like, okay, say it was 1 1 in the first two. So yeah, I mean, this is like your complete string, whatever you will have over here, and then you will consider just one column, right? That one column is basically your input. So suppose there was no carry, then what should basically happen is like this plus that modulo 2 should at least be this thing. So 1 1 0 is an accepted string, one like 0 0 0 is an accepted string, all of that stuff. And also it should tell us like whether or not we want to carry, right? Yeah. So immediately if the remainders do not match up somehow, then it will go into the Q reject state, right? So both of these will go into Q reject states based on like some criteria which will get defined in the transition function. So your alpha 3, it's a finite set. So like you can define a transition function such that, you know, if it's like 1 1 0, no. So if it's 1 1 1, no, you do not accept it. So you just directly send it to the reject state or something like that. Yeah, that looks about right. It's going to be much more complicated than that, but that's the whole idea basically, that every single time you will check, and if it's, and similarly if it's a Q carry, then it would be 1 1 1 is a valid thing, but yeah, right. So if it's like not valid, you just send it to the reject state. Actually, you know what, you don't even need this q accept stuff over there. Make these two the final states. Yeah, that looks correct. But actually no, don't make these two the final state, just make this one. So what should basically happen is like, in the end, so once you're done with the whole thing, what should happen is, like, it doesn't matter whether or not you have like carried something or you have not carried something. How do I even say this? Yeah, in the end what would happen is, let's just say this is like the last kind of thing for your string, right? You might have a 1 over there, and then you would have probably got a carry from previous whatever, and then this would be 0 0 or something like that. If there's a carry, then both of these should be 0 0, and because it's a last character, right? So it's the last input. Because if not, then of course you would have a input in front of, sorry, after it, so it doesn't make sense for it to be the last. If it's the last and if there's a carry, you have a 1 over there and I have a 1 over there, right? Right. So yeah, what was I going to do? What was I going to do though? Yeah, right. So if there's a carry, you are in the carry state, and now the input is like 0 0 1, so you are over here, right? You know where to jump to. You just have to jump to this, because the next time you don't have to carry anything. It's just like 1 plus 0 plus 0, you just get 1, you don't have to carry anything. So now you are at this state, and well, the string gets ended. Now there's nothing over there, so you are done basically. That's how it should be. If you are carrying something, then that pretty much means that your string hasn't ended, because I mean, if you're carrying something, there has to be something over here, right? So it's going to continue like that. So this is the only final state. This is not a final state. Yeah, that looks right. So you can define a transition function for this and that, not separately, it's going to be a single transition function, but like, you know, you have the q and sigma stuff. So yeah, for each of the things in sigma 3, you define what's going to happen if it's at this stage and if it's at this stage. So that's the whole idea. I won't be doing like a whole derivation of what it's supposed to be and all that, but I guess you already got the gist of it, that this is how it can be done. Yeah, I'm not going to write down the whole transition function. Nope. And where to start, by the way? Well, of course, initially you haven't actually carried anything, so you just start over there. Easy. Now, of course, 0 0 0, that's a valid input. In that case, you don't like switch to anything, so just like over there. So as long as you're staying there, you don't have anything to worry about, right? Like, you know that the input you provided is correct. But like, suppose you have a carry, you have to go to this state at that point, and then if something is wrong, you have to go to the reject state. Similarly, over here you have to go to the reject state. So it's useful. Like, this, everything that we're learning is kind of useful. It's not that bad. Okay, so we are supposed to say that B reverse is regular, which we already did, because we'll be reading it from this side, so from right to left. But if you want to read a string from right to left, you are essentially reading the reverse of the string from left to right. So that's why we are actually doing B reverse. So B reverse is easy, and B reverse is regular. That means B itself is regular. Cool. Next. So let this contain all columns of zeros and ones of height 2. A string of symbols and two rows of, okay, considering each of yeah, okay. Right, so once again, this gives 2 rows, zeros and ones. Consider each row to be a binary number. Fine. And let C be this thing. So once again, you can assume the result in 31, which is the reverse thing stuff. So now what you want to prove is that this language where the bottom row is 3 times the top row, as binary numbers of course, that is regular, right? And then you can build a DFA for doing that. Okay, so 3 times of that. in binary it's like 1 times of that, essentially, right? So what you're basically saying is that you have some number, it's like 0 1 1 whatever, and then you just shift this number to the left, like 0 0 1 whatever, and then you add these things. Yeah, that's what you're saying. Now how do we apply this shift operation? Oh, that's kind of complicated. Wait, so what are the carry states at this point? Like how big could it be that you are carrying? Ah, that's kind of a complicated thing. Wait, you're doing it 0 1 1. That's going to be tough. Okay, this is going to be different. Firstly, it's in binary, so you don't do it the way it's normally done. You have to shift the thing. How? How do you shift it? Like you have to retain, right? So if you're doing like this, okay, so think about it. Your input is something like that. Maybe it's 0 0, but whatever the last thing was, oh, that's also sort of a carry, isn't it? Yeah. Right. So if this was your string, maybe you had 0 1 over there or something like that, I don't know. 3 times of that. It's 1 1 times of that basically. So this top string, it had 0 0 over there, right? You would know that now if this is in the how do you call this thing? If this is the addition that you'll be doing, right, then you would have to have this thing, because it's like you had a string something like that, and now this one is where you'll be doing the addition. So the one which was shifted, the shifted string would have this 0 over there, right, and then you would have 1 or something like that, well, a 0 in this case. Fine. So you basically just have to remember what this was, and that can be once again done with a 0 state and a 1 state. So you have a 0 state and you have a 1 state. The 0 state basically says that your last, okay, wait, but there's also carry state involved, right? Because it could be that 1 1 and that gives you carry. Oof. So you have to remember a bunch of things. There's going to be actually 4 states involved. So you have to remember what was the last, like in this string, what was the last bit, right? You have to remember that, because that's the one you'll be adding it, right? You also have to remember what was the carry bit, right? In the last addition that you performed, you carried on something. So remember what that was. Also remember what the last bit was and what the initial bit is. So what the current bit is. Using these 3 things, you would be doing something. And all you can read right now is, all you can read right now is just the initial bit, and of course the bit that addition is supposed to give. So the way this would work is you have 4 states. So the states would, I'm just going to label it as 0 0, 0 1, 1 0 and 1 1, where this state basically represents that the carry is 0 at the same time the last bit was 0, right? And then you would have transitions for each of these states, and each of these would give you a rejection based on, you know, some criteria. Like if it read and it saw that, oh, the addition does not give you this thing, then it like rejects basically. What's going to be the initial state? Initially you haven't actually carried anything, and your last bit will just say 0, right? Yeah, I guess that's the thing. So this would be our initial state. And also the final state, what's that going to be? In the final state, you would have carried something, then come on, think about it. Last addition that you perform that's supposed to give you a 0 carry, right? Yes. Yeah, that's supposed to give you a 0 carry, right? And come on, think about it. What's the last addition that you perform? I mean, this would be the thing. So over here you would just have a 0 carry, right? Because this has to be the last addition. What? No. No, 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 no. This is the last addition, right? So the carry produced due to the last addition. That's what we're talking about. So that's going to be 0. Cool. And what would be, the, what is it called? What would this bit be? Yeah, this one. Well, that's also going to be 0 because we know we just like shifted the whole thing. So this would be 0. Wait, what? Oof, it's getting all complicated now. Wait a second. Am I sure I'm doing this correctly? I have this shifted. That's the previous one. This would be some kind of end which you don't want to use. This one has this one before that, right? The shifted one is the previous one, so you initially start off at 0. Makes sense. So this also has to be 0, but you do not actually have it, right? So this is not the last addition that you would be doing. Last addition that you would be doing is this, basically. Yes. Right, because this is the last character in the string, right? And this is the one that just came before it. Okay, there might be a carry, there might not be a carry for this addition, but essentially what's supposed to happen is that after that you could have a carry, right? You could have a carry or you could not have a carry. That does not matter. It's like in this addition you should not. How do you make sure that this 0 is like in place? It doesn't make sense. Okay, this is your last bit, right? Oof, come on, think about it. Oh, so it should be going to a node that produces no carry. I get it. I mean, this could, for all we know, could just be 1, so that's not a problem. It should be going to a node that does not produce a carry, right? But wait a second, this doesn't even make sense. Something's just wrong about this, because I know for a fact that this length, it would be bigger than this length, and yeah, for example, if this was 1 and then over here you did some addition and that gave you a 1, then it would actually go over here, so you would have 0 0 and then 0 0 over there as well, so something like that. So this would be 0, this would be 0, this would be 0. That's how the addition should be. So that's, yeah, that's right. That's how it should be. And this got transposed a bit. Oof, this is complicated. So you know for a fact that in fact this has to be 0. Right, that's just the thing. We know for a fact that this has to be 0. Because if it's not 0, then you just progress it and it's all messed up at that point. Right. What if this is 1? Well, it could be 1 and then you, yeah. So you know for a fact that this has to be 0. So the last bit is, or the first bit, depending on how you think of it, is always 0. So when do you terminate? you terminate when there's no, so this is actually the last addition that it will perform, and this will be 0, and the last bit that you have, well, that could be 1 or that could be, it could be anything really. So if it's 1, you should not, like, yeah, okay, it doesn't matter, it doesn't matter whatever the situation is. The fact is, this last thing, it does not generate any carry. And when does that happen? When it happens when this machine enters a state where the carry is 0. So this and that, these are the only two valid things, right? And yes, this could be 1, sure. Oof, am I messing up something? Could it be that the last bit is 1 after it enters this state? No, it's not possible, because we know that this was the last bit in red, so it has to be 0. So this is the only final state possible. Yes, that's how it's supposed to be. Cool. So there's only one final state, which is also the initial state. That's just a coincidence. It wasn't really necessary. But yeah, that's just how it works. Cool. So yeah, it is in fact regular. And this is the reject state. Right. Then you have some interlinking going on, which like it's given by the transition function, but like let's just not talk about it. And next question. Okay, let this be the same as in problem 1.33. Consider each row to be a binary number and let D be equal to the set of W such that the top row of W is larger number than is the bottom row. Okay, show that D is regular. Okay, shouldn't be a problem. It's a larger number, isn't it? So now you want to be doing subtraction. Okay, you don't actually even want to be doing subtraction. It's something like you start reading from the left. Normally this time, in the last two questions we were doing the reverse and then saying it's regular. We won't be doing the reverse over here. We start reading from the left, and wherever it happens that, yeah, okay, right, so it's the set of all such W such that the top row of W is a larger number. So you should just encounter a 1 in the top row before you encounter a 1 in the bottom row. So if you ever encounter this input, it means nothing, right? As long as you're encountering this, so just think about it. You start wherever you start. You keep encountering this stuff, it means nothing. You keep encountering this stuff, it means nothing, because we don't have any kind of comparison. But the moment that you encounter 1 0, that means, yeah, it's a valid string. So with 1 0, you just finally get to the accept state. And if you never encounter, if you encounter 0 1, that just means it's not a valid state. So you just go to some reject state, and that's how it should be. Okay, next question. Next question is, hey, is that the same thing? Okay, no, 35. Oh god, okay, it is in fact the same thing. So once again, it's the same as in problem 1.33. Consider the top and row to be strings of zeros and ones, and so now these are not binary numbers, fine. And let E be all W such that the bottom row is the reverse of, oh my, yeah, E would not be regular. It makes sense. So you would need a stack for this, essentially. Wait a second. How would you even do it with a stack? You would need 2 stacks actually, right? You would need to read it 2 times. Yeah, that's kind of problematic. Yes, so E is not regular. Maybe the pumping lemma will help us with this. Right. So you want to pump it all the time. It's the reverse of it. Oh, if it's the reverse of it, then this means then the number of ones would be the same. That's one thing, right? yes, you pump it and then you get number of ones to be same. So essentially just want it to be such that you get a section where you do not have the zeros and ones to be equal, right? If I can just provide a counter example of something that is in it and it cannot be pumped, that would be just so good, right? Yeah. Okay, how about this string? Let's try it out. So you just do like 0 0 0 0 0. I should actually not write it like that, but yeah. So you do 0 1 and then you do 0 1 again, and then you just keep going 0 1 and some number of things, I don't know, and then the same number of 1 0 1 0 1 0. This is certainly in the language, right? Yes, it is in there. Now say you have a section of this and then you want to pump it. Is it possible that you pump it and then you get the reverse of the top row being the bottom row? I mean, it's certainly possible. It's just going to be symmetric at that point. Oh god, this is complicated. If it's the reverse, then the number of zeros and number of ones should also be the same in both of these, right? So you cannot have an uneven cut which has more ones than zeros, and then you would pump it and yeah, the first one has more ones than zeros and something like that. So that wouldn't make any sense. So the only way you would be able to do this is if you had a symmetric cut, sort of. So then the way you would be doing is like 0 1 1 0, and then once again 0 1 1 0 or something like that. So would this be the reverse? I mean, consider you have pumped it. Well, it's gonna be an even thing, an even number, so you can always like cut it like that. Yeah. Okay, so no, it does not seem to be the reverse, is it? It is actually 0 matches with 0, 1 matches with 1, 0 matches with 0, and 1 matches with 1. Okay, that's for 2. What about for 3? 0 1 1 0. I mean, you would always be able to do this, right? 0 1 1 0. Oof, no, you would always be able to do this. This is going to be stupid. So this was a bad counter example. There has to be some way of proving it's not regular, right? Is that it's a reverse of that? Come on. Just need a counter example. Just need a counter example. Such that you are not able to pump that. Okay, this is hard. I never done something like this before. Show that E is not regular. Oof, how? Bottom. I mean, I know for a fact it's not regular because I do not have any way of constructing the machine, but how do I show it's not regular? Maybe it like implies something and then it's bottom row of W is in the reverse of the top row. Well, if that would be happening, then the operation of reversing a string would also happen, like in any F finite automata, which does not happen, right? Yeah. You can't just reverse the input or something. Okay, you can't, right? How do I make sure that this actually works? I don't know. I guess we'll just have to move on and then let 35 stay for a while. Next question is 36. let b and b all a power k such that k is, so a repeated k times, so that k is a multiple of n. Show that for each n bigger than or equal to language we, come on, come on. So what is bn basically? It's just a n star. Yeah, come on, what is this? It's stupid. So it is of course regular. It's given by a regular expression. Alright, next. Cn is all x such that x is a binary number and that is a multiple of n. Okay, multiple of n. That's interesting. Show that for each n we are equal to 1, the language Cn is regular. All x such that x is a binary number. Okay. Right, again, so the string interpreted as a binary number, and that binary number is supposed to be a multiple of n. And I want to show that this is a regular language. Hey, so if it's you know a multiple of n, then it's like what? It's like n plus n and all of that stuff, right? It's basically n repeated with itself a bunch of times. Okay, interesting. Yeah, very interesting. So it's like n times some, so n is like some binary string, okay, and that times of this stuff. So and this could be like varying. Okay. Oof, it's very weird. How do you check if a number is a multiple of a certain number? Okay, how do you check if a number is even? We just check it's 0. Okay, how do you divide by a number in this case? You don't have to divide really. You just, oh come on. There has to be some way that this happens. Oh, come on. Think about it. I do not know. This language is a regular language. The hell. Okay. How do I prove that this is a regular language? So if it's an even number, how do you do that? It's like, suppose you have to show that it's a multiple of 6. Okay, what's the HCF of 2 and 6? Well, that's certainly not a power of 2, so it's going to be stupid. No, this one is hard. It's a multiple of n. So it's going to be doing it in modular. Hey, yeah, that seems sort of right. Hey, okay. I think I might have an idea. So essentially what we're saying when we say that a number is a multiple of n, that we are saying that the remainder of the number when you divide by n is 0, right? So I can get the remainder in a very weird sort of fashion. So you have this string 1, 0, 1, whatever it is. You start out with a 0 state, a 0 remainder, right, which is supposed to be your except state. And then you figure out, okay, so next you're going to add 1, but you're not just adding 1, you're actually multiplying this by 2. So the remainder itself is like getting multiplied by 2. So you're going to go to once again the 0 state basically. Yeah, but then you're adding 1 to it. So you will be multiplying by 2 in any case, but you're going to add 1. So that times 2 plus 1 thing, it only takes into account whether this is 1 or it's 0. So it's times 2 plus 1 or times 2 plus 0. So you can make a transition, like it's basically like q times 2 plus plus sigma. I shouldn't say sigma, I'll just call it like input I. So I, yeah, if it's 0 or 1, right? And q is the current state that we are in. Well, this remainder with n, that is the new state. So actually, like, make a delta function such that this happens, right? And then you just have 0, 1, 2, these states till n minus 1, right? Because those are all the possible remainders, and then you're just like, it's gonna go over these remainders continuously as you progress to the string, and what should happen is that you just end up at 0, and then it's a multiple of n. So yeah, it's actually regular. You can make a machine that does all of this. So right, yeah, it makes sense. This is a regular language. Okay, so that was easy. I thought it was going to be hard, but yeah. So 37 is done. 38, and all NFA M is a 5 tuple that accepts x in sigma star if every possible state that M could be in after reading input x is a state from F. Okay. Note in contrast. Wait, what if every possible state that M could be after reading input x is a state from F? So essentially an all NFA is sort of like a DFA, right? Yeah. It's a state from F. Come on, think about it. So, okay, what? Prove that all NFAs recognize the class of regular languages. Okay, so every regular language can be recognized by some all NFA. What all I essentially want to prove is something like every DFA could be converted to an all NFA or something. But then a DFA is already an all NFA, so I mean, think about it. A DFA is an NFA, but this is very weird. I guess all NFAs are a subset of NFAs, and DFA is a subset of NFA. Sorry, all NFAs. But then even a single DF, like the set of DFAs can recognize the class of regular languages. So that essentially means that the set of all NFAs can also recognize the class of regular languages. Yeah, I mean, think about it. Every DFA can be converted to an all NFA. And that pretty much means that, yeah, every like regular language has an all NFA that recognizes it. Cool, makes sense. We're done. We are actually done over here. Yep. So think about it. A DFA, for a DFA, once you start reading X, there's only one state it can be in. Because there's only one state it can be in, and it is in that state if it's a valid input, it's also in every possible state that it could be in after reading a valid input. Yeah, so we are done. That was stupid. It's just a bunch of wordplay. Next question. The construction theorem 1.54 shows that every GNFA is equivalent to a GNFA with only two states. We can show that an opposite phenomena occurs for DFAs. Prove that for every k bigger than 1, a language exists that is recognized by a DFA with k states but not by one with k minus 1 states. So DFA with k states can recognize it, but not by one with only k minus 1 states. Oh, this example, the CN thing. So it's the set of all languages such that, yeah, this probably, right. Yes, this makes sense. This actually makes sense. Yeah. So this thing, CN is a language that requires necessarily at least n states, right? So it cannot be recognized by something with less states than that. It won't. Yep, sounds good. Sounds good actually. So Cn requires like how many states? N plus 1 actually. Yeah. So we want to show that for every that there exists a language AK such that any DF with k minus 1 states cannot recognize it, right, for every k. So just consider the language Cn minus 1, sorry, Ck minus 1. So just define AK to be equal to Ck minus 1. You know that a DFA with k states can, which is a k plus 1, sorry, which is k minus 1 plus 1, that can recognize this, but it won't be possible for any language with less states to be able to recognize it. It's just impossible, isn't it? Because like, how are you going to simulate? It doesn't make sense. So yeah, that sort of makes sense. Oh, also there's a much simpler example. You know, all those examples we did, like with at least k zeros or at most k of that. So just consider the language where you have um, where you have the you have a specific substring which is of length k. Yeah, you would need k states. You would necessarily need k states to be able to recognize that language. You cannot do that with k minus 1 states. Right, it makes sense. Could you do that with k minus 1 states? I don't think so. For example, just consider the language where you have exactly k ones, right? Could you in any way construct, so like just consider a language like this, and that's it, that's the whole language. You can certainly construct a machine that will, and the alphabet we're talking about is of course 0 1. You can construct a machine which recognizes this language, right, with 5 states, because anything else is just not gonna work. So like I'm telling you, try to construct a machine with 4 states that can recognize this language. It's just not possible, because you have to have exactly 5 states, and there's no way a DFA can count. It can only compare, unfortunately. I've learned that it can only compare. Through all these examples, it cannot count. So yeah, it's just impossible. Just impossible to do it with 4 states. A DFA cannot do it. Okay, cool. So here we go, the next thing. Yeah, okay. Recall that a string x is a, so wait, but how do you prove that this happens? I don't know, but it seems convincing enough for me. Next, recall that a string x is a prefix of a string y if a string z exists where xz equal to y, and that x is a proper prefix of y in addition if in addition x is not equal to y. What? Okay, if the x is a string. Oh, so right, the z could be epsilon, and that's for proper, right? A proper string would not have z equal to epsilon. Okay, so proper prefix is basically like xz equal to y, but then z is not epsilon. That's it. In each of the following parts, we define an operation on a language. Show that the class of regular languages is closed under that operation. So no prefix of a is all w in a such that no proper prefix of w is a member of a. No proper prefix of w is a member of a. Wait, what? Oh, so you're talking about strings in A which have all of their prefixes not in A. I get it. And you have to show that this is regular. Oh my god. Maybe non-determinism would help. Non-determinism probably will help in this. So suppose you're putting in a random input into some machine which has this language, no prefix of a. What would you expect? If it's in a, I mean it has to be in a, right? So one of the machines that you would put inside the machine is a, right? So you just start with W and then you say, okay, well, if A reaches the final state, cool, that was in A, right? But if it just happens that you reach the final state before and then you reach it again, then that's to say that there was a prefix of W such that I get it, I get it, all right. Oof, that's kind of a weird problem, isn't it? So you should not be able to reach the accept state twice. If you ever do that, you are in some deep trouble. Okay. How do you do that? So once you reach the accept state of A, that is, what should happen is if there's any more stuff going on, if there's any more character, you trash it. You trash the whole string. So you have some machine, some DFA will say that it has an input, it has some final states, whatever, and then you input it in it, right? For each final state, what you'll do is, if it like the string is ending, well, cool, you are done. But all the back arrows that you were having, delete all of them, and instead, so yeah, right, you can only enter it, you can never leave this final state. So delete all the back arrows, and instead what you want to do is put an arrow like this for every such final state. Any character from alpha, that will just make it rejected. Actually, yeah, you don't even need this arrow. So any character from sorry, not alpha, from sigma, it will just make it reject it completely. And yeah, that's, I guess, the new machine which recognizes the no prefix a thing. Wait. Yeah, okay, yeah, it does. No proper prefix of W. W still has to be in A. So if the prefix of W was in A, then go for that instead. And then yeah, you just only have the prefixes in it, right? Then you have another operation, no extend of A, which is all, so of course we just proved that it's regular by making a machine. Then you have no extend of A, which is all W in A such that W is not the proper prefix of any string in A. So wait a second, if it's a proper prefix of any string in A, that's to say that, oh wait a second, okay, wait. It's all W in A such that W is not a proper prefix. So firstly, W is in A, okay, that's one of the conditions, and also it's not a proper prefix of any string in A. Now if it was a proper prefix of some string in A, right, then wait a second, of any string in A, that's weird. Wait, what? So like no prefix of A, well, it's completely different from this thing. Yeah. Let's wait a second. Think about it. So now you have another character. Oh, so it should be something like with any character, now you cannot get back to the thing, right? Okay. Just wait a second, think about it. Okay, I don't know where the song is coming from. But what should essentially happen is you want to somehow check in a way every like possibility that could be after W. So there's some non-determinism that's coming in, right? What do you exactly want to be doing with it though? So if you ever reach the state again at that point, you gotta trash it. Okay. I guess I'm getting it. Okay, so it's going to be something like this. So let's just say that you have a machine M that recognizes A. I'm thinking of a machine M dash which does not have any back arrows from the final states. And the final states themselves are not the final states. Okay, they are still the final states, fine. So M dash is what we use essentially to like construct the no prefix A, right? We just make every final state of M dash point to a reject state in case any other character comes in. Now what we want to do is you will construct an NFA which is basically M dash. Yeah, I mean like convert a DFA to an NFA. Every DFA is an NFA in the first place. So just think of it as an NFA. Now what you want to do is, you know, these are not the final states anymore. You cannot be sure that these are the final states. Instead, oh come on, this is kind of complicated. Come on. Right. I get it. So this is what you have to do. You will use M again, right? So this is M, this is M dash. Now you will say that the final states of M dash will strip them of being like having a status of being the final states. Okay. And so something has reached the so-called final states of M dash, right? Now what should happen is you're going to jump into M, like jump into M, but not like that, not with the initial state. You'll jump in the corresponding final state, right? And M still has all the back arrows and everything, but you'll change it again, and you'll change it such that the back arrows now all have, you know, sigma on them, as in there could be something that does it, something actually not even sigma, it's like epsilon on them, right? You essentially, all you're saying is like there is some character you can input such that this would go from the final state to something else. And if all of that, like you go through M dash, you do whatever you want to do, and then if you once again reach a final state, that's problematic, right? That's kind of problematic. So you do not want it to be reaching that state. So essentially what you want is it to stay in the remaining part of M dash. So these states will now all be accept states. Yes, it's very weird, but that's just the way it is. Because if it can ever reach back to this, yeah, it's kind of problematic. Okay, yeah, this is kind of nice. Okay, wait, no, but would it also not just be in the accept state? I mean, yeah, that's a problem with using epsilon inputs, isn't it? Oof. How do you make sure you trash it correctly? Okay, I'll actually think about it, take a break. So I'll see you guys in the next video. Bye.